Before the stars, before the galaxies, before even time as we know it, there was silence. Then, everything changed. In a fraction of a second, the universe burst into being. Not into space, but as space. Not in time, but creating time. This was the Big Bang. Not an explosion in space, but the birth of space itself. From an infinitely dense point, the cosmos began to expand. Not into anything, but stretching the very fabric of existence. And in those first tiny moments, the laws of physics were written. Gravity, electromagnetism, the forces that would go on to shape every atom, every star, every living thing. But that was only the beginning. As the universe cooled, particles formed. Hydrogen and helium were born. And over time, hundreds of millions of years, those simple elements collapsed under gravity, igniting the first stars. And in those stars, the magic happened. Nuclear fusion forged new elements: carbon, oxygen, iron, the building blocks of life. When those stars died, they scattered their ashes across space, enriching the cosmos with the materials that would become planets and people. You, me, everything we know, made from stardust. And yet, even as we gaze up at the night sky, few of us grasp the scale of the story we're a part of. Our Earth is a small rock orbiting a medium star in a quiet corner of the Milky Way. But the Milky Way itself is just one of over 2 trillion galaxies, each with billions, sometimes trillions of stars. Between them, voids of darkness, oceans of nothingness stretching across unimaginable distances. And still, we dare to ask, how did this all begin? Where is it going? And, most haunting of all, why is there something rather than nothing? These are not just scientific questions. They are human questions. They're questions about meaning, about origin, about destiny. For centuries, we've tried to answer them with myth, with philosophy, with observation. But now, for the first time in history, we have tools that allow us to look back, not just years or centuries, but billions of years. We can see the faint glow left over from the birth of the universe, the whole cosmic microwave background. A silent whisper of light stretched by time, still echoing across space. We can map the expansion of galaxies, the structure of dark matter, the pull of dark energy. We've sent telescopes like Hubble and James Webb beyond Earth's atmosphere to look not just farther, but deeper. We're no longer guessing, we're uncovering. And as we do, we realize that the universe is not static. It's dynamic, evolving, alive, in its own cosmic way. Galaxies collide and merge. Stars are born and die. Black holes devour matter and warp time. And somewhere, in the midst of all this vastness, a fragile species on a pale blue dot begins to wonder and to understand. That's where you come in, because this series, this journey through space and time, isn't just about stars and numbers. It's about you. Your atoms were forged in stars. Your mind can comprehend galaxies. You are, quite literally, the universe trying to understand itself. And in the episodes to come, we'll explore how the cosmos began, how it works, and how it might end. We'll travel through the history of time. We'll dive into black holes. We'll sail across the cosmic ocean. And we'll confront the deepest mysteries science has ever faced. But first, let's begin where all good stories begin. At the beginning. Because to understand where we're going, we must first understand where we came from. So take a breath, look up, and remember, you are part of something vast, something ancient, something beautiful. You are part of a story written in stars. And that story is just getting started. This isn't a temporary effect. It's baked into the structure of how space behaves. When we speak of the observable universe, we're referring to the region from which light has had time to reach us since the beginning. It's a sphere around us. Not because we're at the center of the universe, but because we're at the center of our own past light cone. Every observer in the universe has their own observable universe. If there's someone right now, halfway across the cosmos, lying quietly on a planet circling a distant star, their sky looks different. Their horizon surrounds them, centered on their own place in space and time. The edges don't match ours. The stars they can see may include some we'll never witness, and vice versa. It helps to think of light not as something instantaneous, but as something that travels. We forget that because light moves so fast. On Earth, it's almost immediate. From the Sun to the Earth, about 8 minutes. From the Moon, a little over 1 second. But in the vast reaches of space, light becomes a slow messenger. When you look into the night sky, you're not seeing stars as they are now. You're seeing them as they were, sometimes hundreds, thousands, even billions of years ago. Some of the stars in your night sky no longer exist. Their light, still in transit, tells a story from long ago. Our observable universe is defined by how far that light has had time to travel since the Big Bang, about 13.8 billion years. But because space itself is expanding, that distance is now more than 46 billion light-years in every direction. It's as though the universe isn't just old, it's elastic, like a balloon stretching out, carrying distant galaxies with it. Not only are galaxies moving away from us, but some are moving faster than the speed of light, not through space, but because space itself is expanding between us. That means some galaxies have already crossed a kind of cosmic horizon. No matter how powerful our telescopes become, their light will never reach us again. It's like watching a ship disappear into fog, sailing into a sea from which no signal will return. Still, the knowledge that we each stand at the center of our own observable universe is not isolating. It's poetic. It means the cosmos wraps uniquely around you. The light reaching your eyes is yours. The map of stars you carry is unlike anyone else's. Every creature capable of looking up is given a different patch of eternity to gaze upon. That idea, gentle and vast, is part of what makes space so moving. It doesn't shrink us, it situates us. So the next time you look up at the stars, remember this: you are not just observing space, you are participating in it. You are woven into its fabric, stitched into the ever-expanding story of the universe. And that is a wonder worth pausing for, not beyond our ability to imagine. That's where we are right now, at the edge of the known. Not because we've reached the end of space, but because we've reached the end of light. And what lies beyond that? That's where we're headed next. It's a strange thing to wonder how far forever really goes. The question sounds innocent, like something a child might ask while lying on the grass, staring up into the night sky. But the longer you sit with it, the heavier it becomes. It's not just about what we can see. It's about the nature of everything that might exist, even if no one is there to observe it. You've probably heard the universe described as infinite. The word is used often, in classrooms, in books, in quiet conversations about space. But infinite doesn't simply mean very big. It means something more profound. No edge, no boundary, no ending. A space that stretches on, not just for billions or trillions of miles, but without limit. A place without a finish line. That kind of idea can twist your thoughts into knots. How can something have no end? And if the universe does end, what comes after that? More space on a wall? Nothingness? Physicists have asked these questions too, not just with awe, but with mathematics. And the truth is, we don't yet know the shape of the entire universe. The observable part, the region from which light has had time to reach us, is just a small bubble in a much larger structure. It's like looking at the ocean through a porthole. You can see only a circle of water, framed by your window. But beyond it, the sea stretches far beyond your view, perhaps endlessly. Some theories suggest that space might loop back on itself. If you traveled far enough in one direction, you might eventually return to your starting point, like walking around a globe. In that case, the universe would be finite, but unbounded, like a sphere in 3 dimensions. Other theories leave open the possibility that space is truly infinite, that no matter how far you go, there's always more. More galaxies, more stars, more empty reaches of vacuum waiting to be crossed. In that scenario, our observable universe is like a single pixel on an endless canvas. And yet, even if the universe is infinite, we may never be able to observe it all. The expansion of space is accelerating, driven by something mysterious called dark energy. That means that distant galaxies are moving away from us faster and faster. Some have already crossed a horizon beyond which their light will never reach us. Not in 1 trillion years, not ever. This puts a limit on what we can know. It draws a boundary, not to the universe itself, but to what's accessible to us. We live inside a growing bubble of information, surrounded by a sea of the unknowable. But that, too, is beautiful. Because what lies beyond the edge of light isn't nothing. It might be more of everything, more stars, more galaxies, maybe even more versions of us. The idea that the universe goes on, whether or not we can see it, gives space a kind of quiet majesty. It means that reality is bigger than comprehension, that there's always more to wonder about. So, what lies beyond the edge? Possibility. Things are more sparse out there. If the universe is truly infinite, that patchiness likely continues far beyond what we can observe. There could be vast regions with more stars than we've ever imagined, or stretches with almost none. Immense cosmic voids, hundreds of millions of light-years across, where nearly nothing exists at all. And these voids weren't carved out or erased. They simply happened, like ripples that never caught up with the rest. Left behind by chance, by fluctuations in the infant universe as it cooled and stretched and found shape. These empty spots are reminders that randomness plays a part in everything. But here's where the infinite gets even stranger. In an infinite universe, not only is everything possible, everything that can happen will somewhere. Given enough space and enough time, matter will eventually arrange itself in every possible way the laws of physics allow. Every type of star, every strange galaxy, every version of a planet, and yes, even versions of you. Not just lookalikes, but exact duplicates, you standing somewhere else in the universe, thinking these same thoughts, blinking at the sky in the same way, in a room that mirrors yours, atom for atom. Not because the universe intends to repeat itself, but because, statistically, it must. This idea doesn't arise from science fiction, but from mathematics. In an infinite cosmos with finite particle combinations, patterns must repeat. Even randomness, when stretched far enough, creates repetition. The implications are mind-bending. A multiverse, not in alternate dimensions, but right here, spread out across inconceivable distances. It might sound like fantasy, but in cosmology, if something isn't forbidden by the laws of physics, it's considered allowed. And in a universe where everything allowed can happen, we're left not just to ask what's out there, but who. Still, we may never reach those distant duplicates. The cosmic expansion keeps pulling them farther away. The universe might hold infinite yous, but they're beyond contact, echoes in a vast silence. And perhaps that's a good thing, because this version of you, right here, right now, is unique in its experience. Even if other versions exist, none are living this moment exactly as you are. That gives weight to now, to presence. The idea of an infinite universe doesn't diminish you. It multiplies your meaning. It means that this tiny moment, floating on a speck of dust in space, carries echoes that ripple across eternity. Your laughter, your ideas, your curiosity, all of it woven into the fabric of something far greater. When you look at the night sky, you're not just seeing stars. You're glimpsing the possibility of everything, and that in itself is beautiful. So maybe the universe doesn't just stretch forever in distance, it stretches in meaning too. Reaching the speed limit of the universe is not just difficult, it's fundamentally impossible. Not because we haven't figured out how to break it, but because it doesn't break. The speed of light is more than just a fast number. It's the backbone of how reality operates. As you approach the speed of light, strange things begin to happen. Your mass increases, requiring exponentially more energy to keep accelerating. Time, from your perspective, begins to stretch and slow. At the ultimate limit, the rules of physics twist into a paradox. The universe, in its precision, simply refuses to let you go faster. That's why, when we talk about what lies beyond the observable universe, we're really talking about a horizon, a boundary drawn not by space itself, but by time and this unyielding speed. There may be stars just past that horizon, whole galaxies, entire cosmic structures, but we will never see them. Not because they've vanished, but because their light hasn't arrived yet. And more critically, it might never get here at all. Here's why. The universe isn't static, it's expanding, and that expansion is accelerating. That means the very fabric of space between us and those faraway objects is stretching faster than their light can travel to us. Like a message lost in a rising tide, the signal never makes it across. It's as though the cosmos has sections already drifting beyond our reach, not erased, not destroyed, but removed from our experience, forever sealed behind a boundary of light and time. Think about that. There are regions of the universe that, for us, no longer exist, not in reality, but in our ability to know them. They may continue, untouched, forming stars, colliding galaxies, birthing planets. But for us, they are gone. They might as well be invisible. This isn't speculation, it's measurable. Astronomers have identified galaxies moving away from us so quickly that their light will never reach us again. The more time passes, the more the observable universe shrinks, not in size, but in accessibility. It's like being surrounded by islands in a fog. Some you can reach, others are already fading into the mist. You know they're there, but you'll never touch them, never see their lights flicker again. In a very real way, our universe is slipping away, bit by bit, like pages torn from a book we can never reread. Each moment that passes locks another chapter beyond recovery. But within that limitation lies a kind of beauty, because what we can see is extraordinary. The galaxies still within reach are windows into the early universe. Every photon that lands in our telescopes is a message sent across billions of years. A whisper from ancient stars, a glimmer of creation's past. And there's something powerful about knowing we've captured even a piece of that. So while we may never see the entire universe, what we do see reminds us of how much there is to discover. How precious our view really is. How miraculous it is that light from so long ago can still find its way to us. In a universe defined by limits, our vision, however finite, is still a miracle of time, motion, and chance. It defines the border between what is known and what is still waiting just beyond reach. From this point, our journey turns to light, and what happens to it as the universe stretches. Distance, we'll discover, isn't just measured in kilometers or light years. It's measured in time, in how long it takes for light to arrive. And here's the twist. Space itself is part of that story. It doesn't just hold things, it tells light where to go, and sometimes the when to slow down. Not because light resists, but because the very path is shifting beneath it, curving, stretching, folding. Space isn't a blank canvas. It's the painter, the brush, and the motion all at once. You might picture space as emptiness, a passive backdrop, something static, a void that simply is, while stars and galaxies drift like sparks across it. But space is not still, and it's not empty. The more we observe, the clearer it becomes. Space is dynamic. It does things, it expands, it evolves. And here's what's even more astonishing: it doesn't expand into anything. There's no edge it's spilling over, no external arena. Space simply stretches what's already here. It multiplies distances between objects, even as those objects stay still. It's like dots on a balloon. As the balloon inflates, the dots move farther apart, not because they're moving, but because the surface itself is growing. That's the universe. No center, no outside, just more between everything. This idea once sounded absurd, but today it's one of the pillars of modern cosmology. The light we see from distant galaxies has taken billions of years to get here, but during that journey, space itself has been stretching. So the light that left a galaxy 10 billion light-years away may have traveled for 10 billion years, but the galaxy is now 20 or 30 billion light-years away. That's what expansion does. This is why redshift matters. As light travels through expanding space, its wavelength gets stretched too. It shifts toward the red end of the spectrum. This tells us not just how far something is, but how much space has grown since that light began its journey. And here's a quiet, beautiful truth. Every photon that reaches us carries not only a picture of a distant place, but a story of distance changed, of time warped, of space in motion. We're not just watching the stars. We're watching how space itself behaves, how it's moved, and what it's done to the light that passes through it. In this view, the universe becomes more than a place. It becomes a process. Everything is moving, not just objects, but the fabric they float in. Galaxies drift, light bends, space expands, time curves. And we, standing on a small planet circling an average star, are able to witness this dance. We see the signatures of the cosmos in subtle shifts of color, in tiny deflections of light, in whispers from the edge of time. This isn't just science. It's poetry written in gravity and light. So next time you look up, don't think of space as empty. Think of it as alive, as something that stretches and flows, that holds memory in the shape of redshift, that slows light not by force, but by geometry. We are not drifting in a void. We are swimming in something far more mysterious, a growing, breathing, evolving cosmos. And it's still unfolding, one photon at a time. Bit by bit, the cosmos will slip beyond our horizon, not because the stars are fading, but because the space between us and them is growing too fast for their light to cross. The night sky will dim, not all at once, but quietly, subtly, slowly. Entire galaxies will vanish from view, not because they've burned out, but because the expansion of space will outrun their light. Even some of our cosmic neighbors, those galaxies we once called nearby, will drift so far that their photons will never reach us again. Not in a trillion years, not ever. And this isn't happening because those galaxies are moving away in the traditional sense. It's not a race through space. It's space itself that is expanding, quietly, continuously, invisibly, but irresistibly. In a universe without accelerated expansion, the story might be different. Over time, light from distant corners would continue to arrive. New galaxies would be revealed. The observable universe would grow. Our view would deepen. But that's not the universe we live in. We live in a cosmos pushed apart by a mysterious force, dark energy. And because of this force, expansion isn't slowing down, it's speeding up. That changes everything. It means there is a hard limit to what we will ever be able to see. A cosmic event horizon. Beyond that, galaxies are receding faster than light can travel. Not because they're breaking the speed of light, but because the space between is stretching faster than any photon can cross. Imagine trying to walk toward a finish line that moves away from you faster than you can run. No matter how far you go, it stays just out of reach. That's what's happening on a cosmic scale. And this horizon isn't just a concept. It shapes what we know and what we will ever be able to know. Eventually, the sky will contain fewer and fewer galaxies. One day, billions of years from now, distant civilizations may see only their own galactic neighborhood, unaware that the universe was once ablaze with distant light. To them, the cosmos may appear small, static, quiet. But we, alive now, live in a golden window of time. We can still see deep into the universe's history. We can study ancient galaxies, detect their faint light, and piece together the story of the cosmos. We are privileged to be here at this moment, when the light from so much of the universe is still reaching us, when the cosmos still speaks in full voice. And yet, even this voice is beginning to quiet. This realization can feel heavy, but there's a strange comfort in it too, because what we have right now is rare, precious, a view that won't last forever, and that gives it meaning. So when you look up at the stars tonight, remember, the light you see is not just beautiful, it's borrowed, a gift from a universe that is slowly tucking itself away. We are witnesses to a chapter that will never be reopened, listeners to a song whose echoes will eventually fade. But for now, the sky is still full, and that is something worth pausing for. Among the most profound discoveries in cosmology is this. Space was once filled with a nearly uniform glow, a whisper of light stretched thin and soft, rippling gently from the first moments after creation. This light still surrounds us today. We call it the cosmic microwave background, or CMB. It's the oldest light we will ever see, a frozen snapshot of the universe when it was just 380,000 years old. Before that moment, no light could escape. Not because we lacked telescopes or technology, but because the universe itself was opaque. Atoms had not yet formed. Electrons and protons drifted free, scattering photons like fog scatters headlights. There was no transparency, no sight, only heat and chaos. Then, something changed. The universe cooled just enough for atoms to form. Suddenly, photons could travel freely. The cosmos became transparent, and that first light began its journey. Today, billions of years later, we detect that light with precision instruments. It's cold now, just a few degrees above absolute zero. But it still carries the fingerprint of the early universe, tiny variations in temperature that reveal the seeds of galaxies, the structure of space, the geometry of everything. Those slight ripples, just millionths of a degree, tell us that the universe began with quantum fluctuations, amplified by a process called inflation. Space expanded faster than light, smoothing and stretching those ripples into the vast structures we see today. The CMB is a kind of cosmic fossil, a time capsule. It tells us what the universe looked like before stars, before galaxies, before the first atoms cooled into place. But it also marks a boundary, because no light from before the CMB can reach us. The universe before that was invisible, not just in practice, but in principle. There's a kind of wall there, a limit to what photons can tell us, a cosmic curtain drawn over the first instant of time. So how can we look beyond it? Not with light, but maybe with something else. Gravitational waves, ripples in space-time itself, may have been created in the first fractions of a second after the Big Bang. These waves are not blocked by plasma. They pass through everything, and if we can detect them, they could reveal what happened before the universe became transparent. this would be a different kind of observation, a new kind of seeing. Not with light, but with gravity. And it's not science fiction. Instruments like LIGO and future space-based observatories are already hunting for these primordial waves. Their discovery could open an entirely new window into the pre-light universe, a glimpse into time's very beginning. But for now, the CMB is our oldest messenger, a silent echo from the dawn, a map of what space looked like before it grew stars or formed galaxies. It reminds us how far we've come, not just in distance, but in understanding. We started with myths, then with telescopes, then with equations, and now we read the faint afterglow of creation itself, recorded in microwaves, like starlight frozen in time. The universe doesn't speak loudly, but when it whispers, we learn everything. And the message from the CMB is this: we are part of something ancient, something vast, something that has been unfolding longer than any civilization, longer than any star, longer than light itself. And somehow, from a quiet planet orbiting an average star, we've heard that message. We've understood it. And we've begun to ask what comes next. The edge of our observable universe lies about 46 billion light-years away in every direction. This defines a giant sphere around Earth. But don't let that shape mislead you. This isn't because Earth is at the center of the universe. It's because every observer, no matter where they are in space, has their own observable universe, one that stretches out equally in all directions, centered not on some cosmic origin point, but on the point of observation. This horizon isn't about where the universe ends. It's about how far light has had time to travel. From any point in space, what's visible, what's detectable, is shaped by how long signals have had to reach that point. The observable universe is personal. It's not defined by what exists, but by what can be known. What has had time to arrive? And that's the key distinction. Observable doesn't mean visible to the naked eye. It doesn't even mean visible to today's best telescopes. It means that, in theory, some form of signal, light, radiation, gravitational wave, could reach us, given sensitive enough tools. It's about possibility, not perception. It's a boundary not of existence, but of interaction. A line drawn by time and speed. One that separates what can be known from what remains forever out of reach. Not because of our lack of technology, but because of the universe's own design. The observable universe is a kind of bubble, constantly growing. Not because the cosmos is expanding into something new, but because light from farther distances is just now arriving. And as more light reaches us, that bubble grows. Slowly, steadily, patiently. But even this growth has a ceiling. Due to the accelerating expansion of space, some signals will never arrive. Some galaxies have already passed beyond our reach, their messages lost to the stretching of space itself. So we live inside a shifting frontier, a horizon that isn't static but dynamic. And our understanding grows with every new photon that makes the journey. Still, this also means that everything we know about the universe, its shape, age, contents, comes from a limited volume. A volume shaped like a sphere, centered on each of us. For someone on a galaxy 10 billion light-years away, the observable universe looks completely different. Different stars, different horizons, different history. This changes how we think about reality. The universe isn't just out there, independent of us. In a sense, it wraps uniquely around every observer. Each of us stands in the center of our own cosmic horizon, bounded by time and light. And this reveals something quietly profound. Knowledge is always local. Even in the vastness of the universe, our truth is tied to our position, our sky, our time. But that doesn't make it less meaningful. In fact, it makes every view, every perspective, a precious piece of a much larger whole, like windows on opposite sides of a ship, each offering a different sight, but together revealing the full shape of the voyage. So next time you hear someone talk about the universe, remember, what they mean is their universe, their version of the observable, their slice of space and time. And in that way, the cosmos becomes deeply personal. Because the story of the universe isn't just out there. It's also unfolding right here, right now, in your corner of infinity. We live in a rare moment, one where much of the universe is still visible, yet the limits are beginning to appear. The horizon is there. The dimming has begun. But for now, the stars still whisper. From this vantage point, let's continue deeper. Let's explore how time and distance weave together in the fabric of the cosmos. How the journey of light is not a straight line, but a curve shaped by gravity, space, and time itself. How even the shortest path bends. Because to observe the universe is not just to see, it's to listen, to receive, to reconstruct the story of light's long, patient journey across billions of years. We often think of observation as something visual, seeing with eyes, capturing images with lenses. But in truth, it's about interaction. It's about receiving signals, photons, waves, particles, and interpreting the paths they've taken. And most importantly, it's about recognizing this. The edge of what we can observe is not the edge of what exists. It's just the place where the light hasn't arrived yet, and maybe never will. That difference is subtle, but it changes everything. In daily life, we imagine light as straightforward. A flashlight beam moves in a straight line. Shadows fall predictably. Light seems obedient, but on the scale of galaxies, that simplicity falls apart. In the universe, space is curved, not metaphorically, but literally. Massive objects, stars, black holes, even clusters of galaxies, warp the very fabric of space and time. They bend the paths of photons. They twist trajectories. This effect is called gravitational lensing. And it's not theory, it's observable. We've seen galaxies magnified and distorted into arcs. We've watched light curve around invisible masses, revealing things we couldn't otherwise detect. In a way, gravity becomes a lens. It shows us what's behind, what's hidden, what's far. And that makes the universe both more complex and more generous, because light doesn't always take the shortest path. It takes the path defined by the geometry of space. Sometimes it detours, sometimes it delays, sometimes it arrives multiplied, bent into echoes by vast masses. And so when we look at the sky, we're not seeing things as they are, but as they were, filtered through the architecture of space itself. Every star is a story in delay. Every galaxy is a memory warped by the structure of the cosmos. And somehow, we've learned to decode it all. We've built tools to measure those bends, to trace the curves, to map not just light, but the very shape of the invisible. This is the triumph of cosmology, that from one small planet, we've come to understand the choreography of light, the curvature of time, the whisper of gravity. And we've realized this astonishing truth. The universe isn't just vast, it's sculpted, dynamic, alive with motion, distortion, and transformation. And yet, through all that bending and curving, light still reaches us, still tells its story, still carries messages from corners we'll never visit. So next time you look at the stars, imagine the journey of that light, the paths it took, the bends it followed, the ages it endured. And know this, to see the universe is to witness the shape of time itself, and to truly observe is to honor that journey. When you look into the night sky, you're not just looking across distance, you're looking across time. And that's not just poetic, it's physics. According to Einstein's theory of relativity, time and space are woven together into a single fabric, space-time. And at the speed of light, That fabric behaves in strange and beautiful ways. For us, the light from a distant galaxy might have traveled billions of years to arrive. But for the light itself, that journey took no time at all. From the photon's perspective, emission and arrival are the same event. Two ends of a line compressed into a feint. That contrast is more than curious. It's a reminder that time is not absolute. Time is not a universal tick-tock that echoes the same in every corner of the cosmos. Time is personal. It depends on how fast you move, where you are, and what gravity surrounds you. In cosmology, this matters immensely, because when we observe something billions of light years away, we're not just seeing it far away, we're seeing it as it was. The galaxy may have changed, it may have disappeared, but the light reaching us now carries only its ancient story. And here's the unsettling part. We may never know what that galaxy looks like today. Not even in principle. Its now is forever separated from ours by the limits of light speed and expanding space. This is why cosmologists don't just draw maps, they build models. Mathematical frameworks that account for time dilation, curved light paths, and the ongoing expansion of the universe. These models help us answer questions like, when did this light begin its journey? How much has space stretched during that time? What does the structure of space-time say about what we'll see next? Even the idea of now begins to blur on cosmic scales. What does it mean for a galaxy 10 billion light-years away to be doing something right now? What does now mean if the light we're receiving from that galaxy is already 10 billion years old? In some sense, there is no universal now. Every point in space has its own clock, and those clocks don't always agree. This creates a strange tension in our understanding. We want the universe to be synchronized. We want everything to be happening together. But the truth is, reality is layered, staggered, disconnected by vast gulfs of time. And that disconnection shapes how we experience the cosmos. The farther we look, the deeper into history we see. Every image, every signal is an echo from the past. And yet, those echoes allow us to reconstruct the grand story of the universe. We may not know what a distant galaxy looks like today, but we can know how it used to be. And from that, we can guess how it might evolve. We can build timelines, predict collisions, map the rise and fall of galaxies, trace the growth of cosmic structures from tiny fluctuations to vast superclusters. We're historians of light, and in that role, we face a beautiful paradox. The more we learn, the more we realize how little we can see. But even in that limitation, there is wonder. Because the light that reaches us, though delayed, distorted, ancient, is still light, still real, still a message written in the stars. And somehow, against all odds, we've become its readers. So when you gaze into the night, remember this. You are not seeing the universe as it is. You are seeing the universe as it was. And yet, through those fractured fragments of time, you're piecing together something extraordinary. The story of everything. Roughly 380,000 years after the Big Bang, the universe underwent a quiet transformation. For the first time, it became transparent. And in that moment, a picture was frozen. A portrait of the entire cosmos as an infant. That image is the cosmic microwave background. Since its discovery, scientists have worked tirelessly to map it with incredible precision. Satellites like COBE, WMAP, and Planck have scanned the sky, measuring tiny variations in temperature, fluctuations no more than 1 part in 100,000. To the naked eye, the CMB might look uniform, a soft, even glow. But zoom in, and you find a landscape of delicate ripples, minuscule differences in heat and density scattered across the cosmos. And those ripples? They are everything, because they were the first seeds of structure, the places where matter gathered, where gravity slowly pulled atoms together, where galaxies would form, where great cosmic voids would open. Every spiral galaxy, every shining star, every living planet, each began as a whisper in that ancient light. It's strange to think about that the structure of today's universe, the cosmic web of filaments and clusters, all began with these subtle imprints in the microwave background. But those ripples weren't random. They came from something even more profound: quantum fluctuations. In the earliest fractions of a second, the universe was unimaginably small and ruled by quantum physics. Tiny, probabilistic disturbances in energy danced across the infant cosmos. And then, in an instant, inflation began. The universe expanded faster than the speed of light, not through space, but of space. And those tiny fluctuations were stretched, amplified, scaled up to cosmic proportions. What was once smaller than an atom became the blueprint for stars and galaxies. So when we observe the microwave background, we're not just seeing the first light. We're seeing the fingerprint of quantum mechanics etched onto the sky. We're witnessing the moment when the smallest forces shaped the largest structures. It's like reading the universe's baby photo and seeing the genetic code that would define its growth. This is why cosmologists treasure the CMB, because it tells us not just about the past, but about the rules that governed that past. It shows us the balance between matter and energy, the shape of space itself, the age of everything. From those faint ripples, we've calculated the curvature of the universe, its density, its rate of expansion, even its likely fate. And still, it humbles us, because no matter how deeply we study it, the microwave background remains a quiet echo, a message from a time before stars, before light as we know it, before structure itself. It is the oldest story we can read, and one of the most profound. When you look up at the night sky, remember, behind every star, beyond every galaxy, that ancient glow still lingers. It wraps around us in every direction, a halo of history, a reminder that everything we see began as something small, gentle, invisible. And from that gentleness came everything. The ripple became the web, the whisper became the symphony, the flicker became the stars. And somehow, billions of years later, one small species on one small planet learned to read it. Roughly 380,000 years after the Big Bang, the universe underwent a quiet transformation. For the first time, it became transparent. And in that moment, a picture was frozen, a portrait of the entire cosmos as an infant. That image is the cosmic microwave background. Since its discovery, scientists have worked tirelessly to map it with incredible precision. Satellites like COBE, WMAP, and Planck have scanned the sky, measuring tiny variations in temperature, fluctuations no more than 1 part in 100,000. To the naked eye, the CMB might look uniform, a soft, even glow. But zoom in, and you find a landscape of delicate ripples, minuscule differences in heat and density scattered across the cosmos. And those ripples, they are everything, because they were the first seeds of structure, the places where matter gathered, where gravity slowly pulled atoms together, where galaxies would form, where great cosmic voids would open. Every spiral galaxy, every shining star, every living planet, each began as a whisper in that ancient light. It's strange to think about that the structure of today's universe, the cosmic web of filaments and clusters, all began with these subtle imprints in the microwave background. But those ripples weren't random. They came from something even more profound: quantum fluctuations. In the earliest fractions of a second, the universe was unimaginably small and ruled by quantum physics. Tiny, probabilistic disturbances in energy danced across the infant cosmos. And then, in an instant, inflation began. The universe expanded faster than the speed of light, not through space, but of space. And those tiny fluctuations were stretched, amplified, scaled up to cosmic proportions. What was once smaller than an atom became the blueprint for stars and galaxies. So when we observe the microwave background, we're not just seeing the first light. We're seeing the fingerprint of quantum mechanics etched onto the sky. We're witnessing the moment when the smallest forces shape the largest structures. It's like reading the universe's baby photo and seeing the genetic code that would define its growth. This is why cosmologists treasure the CMB. Because it tells us not just about the past, but about the rules that governed that past. It shows us the balance between matter and energy, the shape of space itself, the age of everything. From those faint ripples, we've calculated the curvature of the universe, its density, its rate of expansion, even its likely fate. And still, it humbles us, because no matter how deeply we study it, the microwave background remains a quiet echo, a message from a time before stars, before light as we know it, before structure itself. It is the oldest story we can read, and one of the most profound. When you look up at the night sky, remember, behind every star, beyond every galaxy, that ancient glow still lingers. It wraps around us in every direction, a halo of history, a reminder that everything we see began as something small, gentle, invisible. And from that gentleness came everything. The ripple became the web, the whisper became the symphony, the flicker became the stars, and somehow, billions of years later, one small species on one small planet learned to read it. Imagine a universe still microscopic, just fractions of a second old. Tiny quantum fluctuations bubble and shift, seemingly insignificant. But then, everything changes. Inflation begins. In the blink of an eye, the universe expands at a staggering rate, far faster than the speed of light. And those tiny differences, the random quantum bumps in energy, are pulled outward, stretched across vast cosmic distances. What was once smaller than an atom becomes larger than a galaxy. And those variations? They become the scaffolding of everything. Those slight imbalances in energy density, once too small to notice, become the seeds of structure, the gravitational wells that would eventually draw matter in, the blueprints for galaxies, clusters, and voids. So when we look at the universe today and see galaxies strung together like beads on a thread, woven into massive filaments across space, we're seeing the magnified imprint of those original fluctuations. And when we observe the subtle patterns in the cosmic microwave background, those faint ripples in temperature across the sky, we're looking at the fossilized map of inflation itself, a record of quantum randomness stretched across billions of light years. Inflation didn't just scale up the universe, it smoothed it out. It ironed out curves, flattened wrinkles, set the stage for uniformity. And that's another mystery it helped solve, the flatness problem. In geometry, space can be curved, positively like a sphere, or negatively like a saddle. But when we measure the shape of our universe, something astonishing appears. It's flat. Not perfectly, but incredibly close, within fractions of a percent. That kind of balance between energy, mass, and curvature should be unstable, like trying to balance a pencil on its tip. Yet the universe seems to have achieved it, and inflation may be the reason. Just as the surface of a balloon becomes flatter as it grows larger, the rapid expansion during inflation would have smoothed out any initial curvature. Like zooming in on a massive map, what once looked curved now appears straight. So inflation didn't just seed structure. It also shaped the geometry of the cosmos. It answered questions we didn't even know how to ask a century ago. Why does the universe look the same in every direction? Why is the CMB temperature so uniform? Why is the cosmos so flat? Inflation offers answers. It provides a mechanism for coherence, uniformity, and expansion, all rooted in the laws of physics as we understand them. But perhaps the most poetic part is this: the entire architecture of reality, every galaxy, every star, every breath, is built upon what was once pure quantum noise, a dance of probability at a scale smaller than atoms, whispered into existence and magnified to cosmic proportions. That randomness became reality. That silence became structure. That chaos became cosmos. And we somehow were born into that structure. We emerged from it. We now observe it. And through tools, telescopes, and equations, we trace it backward, piece by piece, ripple by ripple, until we touch the edge of everything. Inflation may be just one chapter in the universe's story, but it might be the most transformative, because it explains not just what the universe is, but how it got its shape, and how everything we know came from almost nothing at all. As we reach the outer limits of observation, the word edge begins to lose its usual meaning. You might imagine the universe like a balloon or a snow globe with a boundary, something we could reach, touch, cross. But the truth is far stranger. The universe doesn't appear to have an edge at all. There's no cosmic wall, no final barrier, no giant sign that says, "End of the universe, turn back." If you could travel in a straight line through space, indefinitely, you wouldn't eventually fall off the edge or crash into a shell. Space either continues infinitely or curves back on itself depending on its shape. But in either case, there is no fence, no drop-off, no outer boundary. And yet, the universe had a beginning. At first glance, that sounds contradictory. How can something have a beginning but no edge? To answer that, we have to reframe the question. The Big Bang wasn't an explosion in space. It was the origin of space. It wasn't like a firework detonating inside a dark, pre-existing void. There was no outside for it to explode into. Instead, space itself expanded. It didn't push into anything. It simply grew from within. Like dough rising, every point moving away from every other point. Not by flying through the oven, but by expanding the oven itself. This means the universe is not expanding into space. It is space, and that space is stretching. So if you ask, what's beyond the edge? The answer is, there is no edge, just more space. This is a hard concept to internalize because our daily experience is filled with boundaries, walls, roads, shorelines. But the universe operates on its own scale with its own rules. Think of the surface of Earth. You can walk in any direction, and you'll never find an edge. You'll simply go in circles, tracing the curvature of a sphere. Earth's surface is finite, but unbounded. Some models of the universe propose a similar geometry. The cosmos might be finite in volume, yet have no boundaries, no edge, just a continuous loop in higher dimensions. Other models suggest the universe is infinite, extending forever in all directions. No loops, no curves, just endless space, populated by endless structure, or perhaps endless nothing. In both cases, there is no cosmic shell, and that's profoundly beautiful, because it means the universe is not something floating in a box. It's not an object inside another space. It is the container. It defines space and time themselves. And when we say the universe had a beginning, we don't mean there was a place, and then the universe arrived. We mean that space and time themselves began. The clock didn't tick before the Big Bang. The ruler didn't stretch. The very concepts of before and outside lose meaning. So when we peer into the cosmos and try to measure its limits, we're not looking for an edge like a fence. We're tracing a shape, a structure, a relationship between time, energy, matter, and geometry. And right now, that shape appears either flat and infinite or curved and unbounded. But in either case, there's nowhere to fall off, no end, no edge, just more universe, more mystery, more of something that contains everything and yet is expanding within itself. And in that boundless expansion, we exist. Drifting through a cosmos that had a beginning but no outer wall. A universe that stretches not into space, but into possibility. So next time someone asks, "Where does the universe end?" you can smile and say, "It doesn't." So far, we've spoken of the observable universe, the bubble of space from which light has had time to reach us since the beginning. But beyond that, there's more space, more time, possibly more matter, more galaxies, more variations of the universe we know. Not a hard edge, but a soft veil, a boundary of knowledge, not of existence. Imagine the observable universe not as a container, but as a growing horizon. Beyond it stretches a region we'll never see, not because it doesn't exist, but because its light hasn't reached us, and maybe never will. Still, we ask, what's out there? Does that realm look like this one? Does it contain stars and galaxies and structures like ours? Or does it change completely? Does it follow the same laws of physics? Or are there regions where things have unfolded differently, where the constants of nature vary, where space itself behaves in strange and unknown ways? We can't answer with certainty. We have no telescope that can peer past the edge of light. No spacecraft can cross that infinite divide. No signal can arrive from beyond a horizon it can't escape. And yet, we can infer. Because the universe we do see is remarkably uniform. No matter which direction we look, the cosmic microwave background appears nearly identical. Galaxies arrange in similar ways. The rules of physics seem consistent. That suggests the universe continues, at least for a while, more or less as we see it now. But further out, all bets are off. It's entirely possible that the observable universe is just one patch in a much larger cosmic quilt, a single bubble in a vast foam of inflating space, a local neighborhood in a sprawling cosmic city. And if inflation continues, in pockets or eternally, then there may be regions unimaginably far from us where the conditions are entirely different, where stars never formed, where gravity works differently, where even time ticks in unexpected ways. These aren't just poetic speculations, they're serious ideas in modern cosmology. The concept of a multiverse isn't about alternate realities with different versions of you. It's about cosmic diversity, about regions of space that are causally disconnected. Not because they don't exist, but because they're too far away for any information to ever cross the void between. They are real in principle, but unreachable in practice. So we live inside a horizon, not of space, but of understanding. Our universe may be just one possibility, one branch, one stanza in a much larger cosmic symphony. And that's both humbling and exhilarating, because it means that every time we look up at the stars, we're not just seeing what is, we're brushing against the limits of what can ever be known. And beyond those limits lies silence. Not because nothing is there, but because light can't reach us, because time isn't long enough, because space is too wide. Still we wonder, still we imagine. And somehow, despite the walls of silence that surround us, we've learned to listen anyway. We model, we theorize. We look at the patterns within our bubble and ask what they might say about what lies beyond. And even though the answer may always remain just out of reach, the question itself is worth everything. So if someone asks you what's beyond the observable universe, you can say this: we don't know. But the possibility is endless. Speculation is part of science. It's the spark that drives new questions, new models, and new curiosity. Some ideas, like the multiverse, extra dimensions, or regions beyond our observable bubble, are fascinating but still unconfirmed. They sit delicately on the edge of theory, beautiful, elegant, but not yet anchored by observation. And yet, they matter, because every question we ask, every measurement we make, helps us narrow the possibilities. It's not about having all the answers, it's about removing what can't be, shaping the landscape of truth through careful refinement. In that sense, science is not just about knowing, it's about ruling out. And with every new satellite, telescope, and equation, we carve away uncertainty. Bit by bit, we sharpen the cosmic picture. And in doing so, we learn something profound. That we live in a universe defined not by the limits of space, but by the limits of information. It's a subtle shift, but it changes everything. Because our boundary, the thing we often call the edge, isn't physical. It's not a wall. It's a frontier of knowledge, a horizon of light, a limit of reach. Everything beyond that is real. But for us, it's unknowable. And that makes the universe feel larger, not just in size but in principle. Because no matter how far we go, there will always be more we cannot see, cannot touch, cannot prove. But we try anyway. It's worth remembering that for most of human history, even the next valley was a mystery. Mountains were maps of wonder. Stars were lamps hung in the sky. We asked if they were close, if they moved, if they were gods. Bit by bit, we replaced myths with measurements. We turned wonder into understanding. Now, we face a new frontier, but this time, the valley isn't 10 miles wide. It's 46 billion light-years across, and growing. We are once again standing on the shore, looking out at an ocean of uncertainty. But this ocean isn't water. It's silence. It's the absence of information. And like all good explorers, we must chart what we can, and accept what we cannot. Still, we push forward. In the next chapters, we'll explore how the universe continues to change, how the accelerating expansion of space affects what we'll be able to see, how galaxies are slipping out of reach, how the night sky of the distant future may look almost empty. But for now, pause here. Stand on the edge, not of space, but of knowledge. Look outward, and know this: you are part of a species that has learned to measure the invisible, to hear echoes from the beginning of time, to ask questions whose answers may never come, and to do it anyway. That is what makes the human mind cosmic. That is what makes the question itself sacred. What if the universe is infinite? Not metaphorically, not spiritually, but literally infinite. Stretching out endlessly in every direction, never looping back, never curving closed, just going on, forever. If that's true, then something extraordinary must follow. Even if space is infinite, the contents within it, matter, energy, stars, galaxies, may not be. The particles, atoms, and laws that shape reality are finite in variety. The number of ways matter can arrange itself is vast, but not infinite. And in an infinite space, any finite arrangement must eventually repeat. It's a strange consequence of simple probability. If you roll dice enough times, you eventually repeat the same sequence. If you shuffle cards endlessly, one day the same hand will reappear. Now imagine that with planets, with people, with you. If the universe is infinite and uniform, then somewhere out there, trillions upon trillions of light-years away, there could be another Earth, another you. Reading this very sentence, with the same thoughts, the same breath, the same moment. Not because nature intended it, but because, given infinite tries, it's statistically unavoidable. This idea sounds like science fiction, but it's not born from fantasy. It emerges from mathematics. Cosmologists have searched for signs of repetition, for clues in the cosmic microwave background, tiny echoes that might suggest space wraps around, for galaxies that might appear in multiple directions, like reflections in a mirrored room. So far, nothing conclusive has turned up, but that doesn't mean repetition doesn't happen. It may simply lie beyond what we can detect, beyond our horizon of light, in regions too distant for any signal to ever arrive. And that's where the idea of the infinite multiverse begins. Not a multiverse of different dimensions or comic book realities, but a multiverse of sheer spatial possibility. A realm where everything that can happen does happen, somewhere. Where every arrangement of atoms, every variation of events, every version of you exists. Not all at once, not magically, but simply as a result of infinite space and time. If that feels overwhelming, it should. It challenges our sense of uniqueness, of meaning. If there are infinite copies, what makes this one matter? But here's a quiet truth. Meaning is not diminished by repetition. The sunrise you saw today may happen 1 trillion times elsewhere, but you experienced it here, now. That moment is still yours. Just as every snowflake is shaped by the same physics, and yet each one is unique, so too is your consciousness, your existence, regardless of who or what might echo it elsewhere. The idea that the universe might contain copies of us is not about reducing individuality. It's about expanding our sense of connection, realizing that we're part of a cosmic probability so vast, so fertile, that it creates every outcome, somewhere. It's also a reminder of humility, that no matter how much we learn, no matter how far we peer, there will always be questions that stretch past our reach. Still, we ask. Still, we wonder. And in that wondering, we become more than observers. We become part of the universe's unfolding thought. So, is there another you out there? Maybe. But the one that matters most is the one asking the question. The one right here, standing at the edge of understanding, choosing to explore. And that, in the end, is something no copy can replace. It begins with quantum mechanics, a realm of uncertainty, probability, and strange outcomes. In this domain, particles don't follow a single path. Instead, they exist in a cloud of possibilities. A particle isn't here or there, it's both, until observed. But what happens when that observation is made? One answer comes from the many worlds interpretation. According to this idea, every quantum event with multiple possible outcomes gives rise to all outcomes, each in its own distinct branch of reality. If a particle could go left or right, it does both. In one world, it goes left. In another, it goes right. And both versions continue, unaffected by each other, parallel and independent. This interpretation paints reality not as a single line, but as a vast quantum tree, constantly branching, forming an unimaginable forest of parallel worlds. It's a radical departure from classical thinking. In this view, there is no wave function collapse, no moment where uncertainty becomes certainty. Instead, all possibilities happen. We just experience one of them. And here's the twist. That includes you. When you flip a coin, when you make a decision, when quantum randomness plays its role, there are versions of you that live out each possible path. In one branch, you moved to a new city. In another, you stayed. In one, you're watching this video. In another, you never found it. The universe, in this framework, is constantly multiplying, but not outwardly. Like in the inflationary multiverse, these worlds don't exist far away in space. They're not cosmic bubbles drifting apart. They exist in a kind of a configuration space, a mathematical realm where every possible state of reality evolves in parallel, governed by the same quantum equations. You can't communicate with these other worlds. You can't cross into them. but they exist, in principle, as natural consequences of the equations that guide quantum systems. Why do some physicists love this interpretation? Because it's elegant. It removes the mystery of wave-function collapse, the odd moment where potential becomes actual. In many worlds, there's no collapse, just deterministic evolution. Everything unfolds according to physical law, but you only experience one thread. You're a passenger in one branch, but the tree is vast. This idea has profound implications, not just for physics but for philosophy. It suggests that there is no single you. There are countless versions, all real, all evolving, all diverging from moments of choice and chance. And while that might sound like science fiction, it's not purely imagination. The many worlds interpretation is mathematically consistent with known physics. It makes no extra assumptions. It fits the data. What it lacks, for now, is testability, because we can't see into those other branches. We can't interact with them. We can only reason that they're implied by the math we trust. So, is it true? We don't know. But it offers a powerful lens, a way to understand the strange behavior of particles, the paradoxes of measurement, and the bizarre probabilistic nature of our universe. And perhaps most humbling of all, it suggests that reality is far richer than we ever dared believe. That while we experience one thread, we are part of an infinite weave. That somewhere, many places, your story is unfolding differently. Not because you chose wrong, but because the universe chose everything. And every possibility has its moment to shine. Some of the boldest ideas in science come not from wild imagination, but from following the math exactly where it leads, even into invisible territory. Take the idea of multiple universes. It may sound like a science fiction add-on, an extra layer painted over reality to make things more dramatic. But in truth, it's baked into the equations themselves. Modern cosmology, especially the theory of cosmic inflation, doesn't just explain the large-scale structure of the universe we observe. It also predicts regions of space we can never access. Regions that inflate differently, evolve differently, and may never intersect with ours. They're not added on. They're results. Natural consequences of the same theory that explains the patterns in the cosmic microwave background and the distribution of galaxies. But here's the tension. What do we do with predictions we can't test? Science is built on a foundation of observation. You propose a model. It makes a prediction. You gather data. You compare. You revise. But what if a theory is extremely successful in all the parts we can observe and also predicts things we cannot? Do we reject those parts, or do we accept them as provisional truths, ideas that may remain untestable but still logically consistent with what we know? This is the current frontier of theoretical physics. The multiverse isn't a theory on its own. It's a consequence, a shadow cast by models that already describe our universe beautifully. To ignore that shadow may be to limit our understanding. To embrace it may be to expand science beyond the limits of experimentation and into the realm of pure inference. It's not just cosmology that faces this challenge. String theory, for example, proposes extra dimensions and a landscape of possible physical constants. Different regions of this landscape may give rise to entirely different universes, with different particles, forces, even laws. We can't observe those dimensions. Not yet. Maybe not ever. But they emerge naturally from the equations we trust. So the question becomes philosophical. What is science? Is it only what we can test, or does it include what we can logically infer from well-tested models? Some physicists argue for caution. If you can't test it, it's not physics. Others argue for boldness. If the model works and its implications are clear, we shouldn't flinch, no matter how strange the conclusion. And perhaps both perspectives are valid. Science must remain grounded, but it must also be curious. It must embrace the strange, without losing its roots in reality. The multiverse may be forever out of reach, but our thinking doesn't have to be. We can build models, sharpen ideas, explore consequences, and look for indirect clues. We can stretch our minds, not just our instruments, and in doing so, we become explorers, not just of space, but of the possibility. This doesn't mean all ideas are equal. Speculation must be tied to evidence, even if that evidence is indirect. But sometimes following the math with discipline leads us not just to new discoveries, but to new questions. Not just answers, but frontiers. And when the best tools of science point to realms we can't see, maybe that's not a failure. Maybe that's the next step. The universe is vast. Our methods are humble, but together they can reveal truths that reach far beyond what light can carry. Picture space. Empty. Vast. But what shape does it have? It's not an easy question, because space is not just a void. It has structure, geometry, curvature, and that curvature defines everything about how the universe expands and behaves. In everyday life, we think of space as flat, like a tabletop stretching in all directions. In this kind of space, parallel lines stay parallel forever. Triangles always add up to 180 degrees. It's the kind of geometry we all learned in school. But space doesn't have to behave that way. Einstein's theory of general relativity tells us that mass and energy bend space, and the total energy content of the universe determines its global shape. There are three main possibilities. 1. Flat space. This is the intuitive universe. Parallel lines remain parallel. The angles in a triangle add up to exactly 180 degrees. Space is infinite, and it expands forever, but never curves. It's what most people picture when thinking of space. 2. Closed space. Imagine the surface of a sphere. Travel far enough in one direction, and you return to your starting point. Parallel lines eventually converge. Triangles have angles that add up to more than 180 degrees. Space is finite, but it has no edges. It wraps around itself. 3. Open space. This one is like the surface of a saddle, curving outward in every direction. Parallel lines diverge. Triangles add up to less than 180 degrees. Space is infinite, and it curves outward forever. So which one are we living in? To find out, cosmologists look at the total energy density of the universe. That means not just stars and gas, but dark matter, dark energy, radiation, and everything else. Einstein's equations link that energy content to curvature. Too much energy? The universe curves inward, closed. Too little? It curves outward, open. But if the density is just right, a Goldilocks value, then space is perfectly flat. And here's what we've learned. Measurements from the cosmic microwave background. Using data from satellites like WMAP and Planck, suggest that the universe is very close to flat. Maybe perfectly so. That doesn't mean it must be infinite, but it does mean that over the observable scale, space behaves as though it is flat. But here's the mystery. Even if the universe is almost flat, it could still be curved just beyond our observational horizon. We're like ants walking on a giant ball, seeing only a small patch, which seems flat. But the ball might curve gently beyond our view. So once again, we face a boundary, not of space, but of evidence. We can only infer curvature from what we can observe. And what we see suggests a flat universe, expanding forever, growing colder, more diffuse. But if it's even slightly curved, either way, it might have implications for the fate of the cosmos. A closed universe might someday collapse. An open one might expand forever. A flat one? It's balanced on a knife's edge. The shape of space isn't just academic. It governs how light travels, how galaxies form, how time flows. It shapes everything. And though we may never walk the edges of the cosmos, or know for sure if there are edges, we can measure the angles, count the photons, and decode the clues hidden in the fabric of space itself. That is the magic of cosmology. We don't need to leave the planet to learn the shape of space. We just need to watch, to listen, to measure very, very carefully. And in doing so, we may discover that space is more than a backdrop. It's a character in the cosmic story. Curved, infinite, finite, or flat, it holds the secrets of our origin and our destiny. For most of the 20th century, cosmologists believed the expansion of the universe was slowing down. It seemed obvious. After the Big Bang, space expanded rapidly, but gravity, the ever-present force pulling matter inward, was always at work. Galaxies, clusters, clouds of gas, every speck of mass tugged on every other. The larger the structure, the stronger the pull. So the natural expectation was this: the universe would keep expanding, yes, but more slowly over time. Gravity, like a cosmic brake, would gradually slow the motion. But then came the shock. In the late 1990s, two separate teams of astronomers set out to measure how the expansion of the universe was changing over time. They studied distant supernovae, exploding stars in faraway galaxies. These weren't just any stars. They were Type Ia supernovae, cosmic standard candles. Their brightness is so consistent that, by comparing how bright they appear to how bright they should be, scientists can calculate distance with astonishing precision. And by measuring how much their light had been stretched, or redshifted, researchers could also estimate how fast the universe was expanding when that light left its source. When they plotted the results, the surprise was immediate. The supernovae were dimmer than expected, not because they were less powerful, but because they were farther away than any decelerating model predicted. In other words, the expansion of the universe wasn't slowing down. It was speeding up. A moment that redefined modern cosmology. This discovery, published in 1998, earned the 2011 Nobel Prize in Physics. And it raised a profound question. What is driving this acceleration? Enter a new concept, or rather, the resurrection of an old one. Dark energy. A mysterious form of energy that doesn't clump, doesn't dilute with space, and exerts a negative pressure. A kind of gravitational repulsion that pushes everything apart. It had first appeared in Einstein's equations as the cosmological constant, a fudge factor he added to keep the universe static before we knew it was expanding. Einstein later called it his biggest blunder. But now it was back, not as a mistake, but as a crucial clue. Dark energy, whatever it is, seems to make up about 68% of the total energy content of the universe. It's not just part of the story, it dominates it. Its effects are subtle, but cumulative. Over vast distances and cosmic timescales, it reshapes the fate of everything. Galaxies that are already far away will become unreachable. The observable universe will shrink, not in size, but in content, as light from more and more galaxies fails to reach us. The night sky will grow lonelier, and one day, if dark energy remains constant, the universe will become a vast, cold, empty void, expanding forever into silence. Some theories propose even stranger endings, where dark energy increases over time, tearing apart galaxies, stars, planets, even atoms, in a final event called the Big Rip. We don't know which path reality will take, because, for all its importance, we still don't know what dark energy is. It doesn't behave like anything else in physics. It doesn't radiate, interact, or form structure. It's everywhere, and yet completely invisible. But it's not nothing. It has energy. It shapes space-time, and it challenges the very foundations of our theories. What began as a small deviation in a few supernova measurements has become a central mystery of modern science. And it all started with a simple question: how fast is the universe expanding? Sometimes the most ordinary questions lead to the most extraordinary revelations. The cosmos, it seems, is not only expanding, but rushing away from us, propelled by a force we do not understand. That is both terrifying and beautiful, because it reminds us that the universe is still writing its story, and we are still here, reading the latest chapter. We may never see the entire universe, not because we're not trying, but because we simply can't. In a cosmos governed by light and distance, there's a fundamental limit to what we can observe. It's called the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. And as the universe expands, especially as it accelerates due to dark energy, this horizon doesn't get bigger. It shrinks. Galaxies that are currently visible will someday vanish from view, not because they cease to exist, but because their light will never reach us again. And this creates a profound problem. If our access to light defines what we can learn, what happens to things beyond that reach? Can we ever know them? Can we say anything meaningful about them? This isn't just philosophy. It's a real problem in observational cosmology. Many of our models depend on light, on measurements of redshift, microwave background radiation, and distant supernovae. But if the expansion of space keeps pulling galaxies apart faster than light can travel, more and more of the universe slips into permanent invisibility. A boundary not just of sight, but of certainty. So, what happens to knowledge? Can we know something that can't be seen? Not now, not ever? Surprisingly, the answer may be yes, because physics is not just observation, it's inference, it's logic. It's the ability to build models based on what we can see and extend them to what we can't. That's how we discovered atoms, electrons, black holes. Each of these started as ideas about invisible things, made visible through their effects. The same may be true for the unreachable parts of the universe. If galaxies behave a certain way, if cosmic structures align just right, if radiation echoes hint at something larger, we can learn about the unseen through what it leaves behind. But this process has limits. As the horizon recedes, we lose data. Fewer galaxies to observe, less information to build on. The cosmic laboratory grows quieter, dimmer, emptier. Eventually, if dark energy dominates completely, the sky will become nearly blank. The only galaxies we'll see are those gravitationally bound to us, our local group. The rest will fade away. And future scientists, billions of years from now, may find no evidence of cosmic expansion at all. No microwave background. No distant galaxies. They may believe they live in a static, eternal universe, just as we once did. All because the light no longer reaches them. This is the strange irony of cosmic knowledge. We live at a privileged moment, a time when the light of the ancient universe still arrives, when we can measure the echo of the Big Bang, when we can see the acceleration of galaxies. But it won't last. Knowledge, like light, has a horizon, and we are watching it drift farther away. That's not a cause for despair, it's a call to wonder, to recognize the preciousness of the cosmic moment we inhabit, to appreciate that in this fleeting window we are witnessing something extraordinary, a universe still revealing its secrets just before the curtain begins to close. What lies beyond the horizon? Possibly entire realms, possibly infinite wonders. We may never reach them, But we can still imagine them, model them, and let their shadows shape our theories. Because in science, what we cannot see still matters. And what we can know depends not just on sight, but on reason, inference, and imagination. Just because we can't see something doesn't mean we stop asking about it. The questions are still valid. The answers, if we have them, must rest on foundations. Sometimes on assumptions, but more often on well-supported models, constructions of logic, math, and experiment that align with what we can observe. It's humbling to admit that even the sharpest human mind is bound by constraints that aren't intellectual, but physical. It's not ignorance that limits us, it's physics. Information can't travel faster than light. And space, in some directions, is expanding faster than that. These two facts together define a hard edge around our understanding. Not because we're not clever enough to cross it, but because reality won't let us. And yet, we've crossed so much already. We've looked into galaxies billions of light years away. We've captured light that left stars before the Earth had formed. We've seen the afterglow of the Big Bang, faint microwaves that whisper across the universe. We've measured the shape of space, the age of the cosmos, the birth and death of stars. We've even inferred the presence of invisible matter and mysterious energy, things we've never seen but can describe with astonishing precision. That's the real miracle. Not that we can't see everything, but that we can see so much. We live in a sliver of space-time, on a pale blue dot, orbiting an ordinary star. And yet from here, with nothing but photons and equations, we've mapped a universe 93 billion light-years wide. Let that sink in. Our tools are humble. Telescopes, detectors, satellites. Our math is centuries old. Our knowledge is evolving, imperfect, incomplete. And still, we've built models that can predict supernovae, black hole mergers, and even the early conditions of the universe with stunning accuracy. Even if the unobservable remains beyond reach, that doesn't make our effort meaningless. It makes it more precious, because we're not just compiling data. We're telling a story written in starlight, in background radiation, in the subtle bending of light as it crosses curved space-time. We're decoding a vast cosmic library, one photon at a time. And yes, there are pages we'll never read, chapters sealed by distance or redshift or expansion. But we still glimpse the arc of the plot. We still see where the story has been, and where it may go. We know that time, like space, has a curvature, that gravity can warp it, that velocity can stretch it, that there are regions of the universe where time flows differently, where clocks tick at unfamiliar speeds. And now, as we turn back to a time, we ask new questions. How old is the universe? How long will it last? Is time eternal, or did it begin, and might it one day end? Is time a straight line, or something more complex? And can we trust our senses, built for seconds and minutes, to understand billions of years? The answers lie ahead. They require not just data, but imagination. Not just models, but perspective. Because to understand time is to understand change. And to understand change is to understand ourselves. So, as we leave the edge of space behind, we now begin the next journey, a journey into the nature of time, its origins, its shape, its limits, and what it truly means to live in a universe that ages, evolves, and remembers.